All right. Good morning, good afternoon, good evening, everyone who's joining in today. Welcome back to the point distributions webinar. Today we have speaking Fritz Pillichshammer, talking about L2 star extreme and periodic discrepancy. After the talk, there will, as in every other time, be tea time just to be able to socialize. So if you want to afterwards, please stay on. Fritz?
Okay, thank you very much, Ryan, for the nice introduction, also for inviting me to give a talk today in your seminar. I will present results about three notions of discrepancies, about three notions of L2 discrepancies, and I will present results about relations between these discrepancy notions. The results that I'm going to present come from joint works together with Josef Dick from Sydney and Eike Hinrichs and Ralf Gritzinger, both from Linz in Austria, from my university. So we study distribution properties of a finite n-element point sets in the d-dimensional unit cube by means of discrepancy, which is based on the notion of a local discrepancy function delta p, which is so p is the point set, capital P is a measurable subset of the d-dimensional unit cube, sometimes called a test set. And the local discrepancy function for this test set B is just the difference between the number of elements from the point set that belong to the box, to the set B, and n times the volume of this set. So this is the local discrepancy function. And different classes of test sets now lead to different notions of discrepancies. And we considered three different notions of test sets, classes of test sets. In the first place, we are considering arbitrary intervals in 0, 1D that are anchored in the origin, which will lead to the usual well-known notion of star discrepancy. Then we extend this class and consider now arbitrary, not necessarily anchored intervals in the d-dimensional unit cube, which will lead to the notion of extreme discrepancy. And as a third class of test sets, we're considering so-called periodic intervals, which will lead to a notion that we call periodic discrepancy. So what do I mean by a periodic interval? First, let me explain in the univariate case, in the one-dimensional case for elements x and y from the unit interval, the so-called periodic interval I, xy, is just the usual interval xy if x is less or equal to y. So if x is less or equal to y, we just take the usual interval xy. If, however, x is bigger than y, so if you have this situation here, then the periodic interval is just the union of two usual intervals, namely this part together with this part. Okay, so this is what we call a periodic interval in 0, 1. Oh, there pops something up, excuse me. And in the multidimensional case for points x and y in the d-dimensional cube, the corresponding periodic interval or box bxy is just the Cartesian product of the corresponding univariate periodic intervals. Here in this picture, you can see three typical examples of intervals from our test sets that we are considering. In the left-hand picture, you see a typical instance of an anchored interval, which is considered for star discrepancy. In the middle picture, a typical arbitrary subinterval of the cube, and in the right-hand side, you can see a typical instance of the periodic interval A and B. Okay, so these are the three classes of test sets that we are considering, and we now study a norm of the local discrepancy function with respect to these three classes of test sets, and as norm we use the L2 norm. So this leads to the three notions of L2 discrepancy. We are studying L2 star discrepancy on the one side, which uses the anchored boxes as test sets, the L2 extreme discrepancy, which uses arbitrary boxes in the unit interval. Here integration is restricted really to only to real boxes, x is less or equal y. And in the third case, the test sets are the periodic subintervals. Okay, so these are the three notions of L2 discrepancies that we are going to consider. Yeah, all three notions of discrepancies are quantitative measures for the irregularity of distribution of the point sets P of finite point sets. But all three notions of discrepancies are also closely related to worst case error analysis of quasi-Monte Carlo rules. And this is an important fact that we will also use later on at some place. For any of the three notions of L2 discrepancies, there exists a reproducing kernel Hilbert space H of functions over the d-dimensional unit cube, such that the worst case error for quasi-Monte Carlo integration in this function space based on the point set P is exactly 1 over n times the respective L2 discrepancy. So this is a relation between numerical analysis on the one hand side and discrepancy theory on the other hand. Maybe you're not so familiar with the notion of worst case error of a QMC rule. I just add here the definition. So we are studying quasi-Monte Carlo integration for functions from the space H. So here you can see a quasi-Monte Carlo rule, which just computes the average of function evaluations over the finite point set P. And we use this quasi-Monte Carlo rule to approximate the integral of the function f over the cube. And we are interested in the absolute error of this cube extended over the unit ball of the function space. And this is the worst case error in which we are interested in. Okay. I will say a bit more on this, and we will also, as already mentioned, this fact in one of our proofs later on. But this is really an important relation and can be exploited at several places. So we are now interested in relationships between these three notions of L2 discrepancy. We ask ourselves, how are they related? L2 star, L2 extreme, L2 periodic discrepancies. Some relations are well known, some are also even obvious, and I want to summarize these known facts in the next few slides. First of all, it's obvious that the L2 extreme discrepancy is always dominated by the L2 periodic discrepancy. This can be easily seen directly from the definition of the two discrepancies, since every periodic box with p of x, every periodic box pxy is just a usual box xy when x is less or equal to y. So from this, it's directly clear that we have this relation. Another result is not obvious, but very well known. It's the famous lower bound of Roth that I think you all know or have seen already from the year 1955. The L2 star discrepancy of any n-element point set in dimension D is bounded from below by log of order log n to the d minus 1/2. So the L2 discrepancy of any n-element point set is always at least of order of magnitude log n to the d minus 1/2. The one is just added here to allow also n equal to 1. So, and of course, we also ask ourselves, is a corresponding result also true for the other two notions of L2 discrepancy, L2 extreme and L2 periodic discrepancy? And this is easily seen for the L2 periodic discrepancy when we use a result of Lev that was later on reproved in one of our papers also, but it was first shown by Lev in the 1990s, namely a connection between the L2 periodic discrepancy and the usual L2 star discrepancy. Namely, the L2 periodic discrepancy can be written as root mean square of the usual L2 discrepancy of the geometrically shifted point set p plus delta, where the root mean square is with respect to all shifts delta from the unit cube. So p plus delta means that we add this shift delta to any of the points of the point set. So the same shift to every point. The root mean square is exactly then the L2 periodic discrepancy. Yes, and now it's clear, applying Roth's lower bound to the integrand here, we see that the same lower bound also holds true for the L2 periodic discrepancy. Another well-known fact is that the L2 periodic discrepancy is essentially the same as the diaphony. Diaphony is another well-known quantitative measure for the irregularity of distribution of a point set that was introduced in the 1970s by Peter Zinterhof, and what is more or less what you can see on the right-hand side up to some normalizing constants. So we have here a weighted sum of squared Weyl sums. So what you can see here, these exponential sums involving the elements from the point set are these Weyl sums that appear in Weyl's criterion for uniform distribution modulo 1. And we square them and sum them up with some weight 1 over rk squared. And this is the diaphony, the square root then of the whole. And this is exactly also the L2 periodic discrepancy. So we can express L2 periodic discrepancy by means of exponential sums. These factors here, these coefficients rk, are for lattice points k are of product form in the multidimensional case, and in the univariate case they are 1 if k is 0, and if k is different from 0, more or less up to some constant absolute value of k. And if one has a closer look on this formula, one can observe already another connection to a numerical analysis. Namely, what you can see here is again essentially, again up to constants, the worst case integration error of a quasi-Monte Carlo rule in a Korobov space of periodic functions of smoothness 2, which is indicated by this square here. So these Korobov spaces are often studied in connection with lattice points. And what you can see here is exactly such a worst case error. So already this relation is an example of a relation between discrepancy theory, discrepancy on the left-hand side, and the worst case error on the right-hand side. What we also can infer from this formula is when we step down for a moment to the univariate case. In the univariate case, there is a well-known connection between L2 discrepancy and diaphony, which is sometimes called the formula of Coxma. The formula of Coxma is an easy thing, just expressing the L2 discrepancy by means of Parseval's identity as a sum of the Fourier coefficients of the discrepancy function, or the squared Fourier coefficients. And the part which is different from the coefficient with index 0 is exactly the diaphony. And remember, we are interested in relations between the three notions of L2 discrepancy. And from this formula of Coxma, we can deduce easily this relation that the L2 periodic discrepancy is bounded by square root 2 times the L2 star discrepancy. And this bound is even sharp. We have equality if the point set is symmetrized, which means that with every element from the point set, also 1 minus this element belongs to the point set. So with x from the point set, then 1 minus x is also in the point set. So this is a symmetrized point set, and for this we have equality. So these are some well-known facts known already before. And now we come to one of our first results. Remember, I already mentioned that it's obvious that the L2 extreme discrepancy is dominated by the L2 periodic discrepancy. Similar result is true for L2 extreme and L2 star discrepancy. The L2 extreme discrepancy is also dominated by the L2 star discrepancy. So from the 3 notions of L2 discrepancies, the L2 extreme discrepancy is the smallest one. The proof of this result is not so obvious like for the previous case, but I would like to give you a short sketch of the proof, also in order to give you an idea of how we can exploit this connection, numerical analysis and discrepancy theory to prove results in discrepancy theory. Okay, so we study we use the Sobolev space W of absolutely continuous functions f on the unit interval to the reals with first derivative in L2. And we study now 2 subclasses of this Sobolev space. The first subclass is the class H star, consisting of all functions from W that vanish in 1. And as norm, we use the L2 norm of the first derivative of it. And the second class is the class H extreme, very similar, with one extra condition, consisting of all functions f from W that vanish in 0 and in 1. And again, as norm, we use the L2 norm of the first derivative. So now, already from the definition of the 2 subclasses, it is clear that H extreme class is a subclass of H star. Okay, this is clear. And it can also be shown that both of them are reproducing kernel Hilbert spaces, and the kernels can be computed explicitly and are given in like the last line here, but that's not so important for the moment. So this needs some work to do. There's a gap here, but it's only want to give you a sketch, the basic ideas. So both are reproducing kernel Hilbert spaces. So far we are in the 1-dimensional case. Now we switch to the multidimensional setting. And here we use tensor products of the univariate spaces, default tensor products, and we obtain again these 2 classes, HD extreme and HD star, and then still it holds that the class HD extreme is a subclass of the HD star, like in the univariate case. And hence it's clear that the worst case integration error of a QMC rule based on the point set P in H extreme is less or equal the worst case error in HD star, because this is a subclass of this here. Okay, so far this was numerical analysis. Now we switch to discrepancy theory. Multiplying this worst case error now by n, then one can express the worst case error, or n times the worst case error in terms of the reproducing kernel. And we remember, we know the reproducing kernels, at least in the univariate case, but also in the multidimensional case, when we are considering default tensor products, the kernels are default products. That's easy and well known in the theory of reproducing kernel Hilbert spaces. And then one can see, again, after some work, but not difficult work, that the left-hand side is exactly the L2 extreme discrepancy, and the right-hand side the L2 star discrepancy. And so we have the relation that we wanted to show, that I announced in the theorem. So this is a short sketch, which should also give you an idea of how to exploit this connection between discrepancy theory and worst case error analysis of quasi-Monte Carlo rules. In the meantime, we also found a second proof of the result, which is based on the Haas series representation of the two L2 discrepancies with the help of Parseval's identity. And from this representation, it's also very easy to see that the relation holds, that L2 extreme is dominated by L2 star discrepancy. It's really, on one side, it's clear that this holds. But one has to compute this Haas series representation. An advantage of the second proof via the Haas series representation of the L2 discrepancies is that with Littlewood-Paley inequality, we can have a similar result also for the LP discrepancies. We don't have less or equal, we have of the same order with an unknown constant, but more or less the same result also for LP discrepancies that can be deduced from the second proof. So the next, we already talked about this Roth lower bound for L2 star and L2 periodic discrepancy. It's not a big surprise, but nevertheless, we know L2 extreme discrepancy is the smallest of the three discrepancies, of the three L2 discrepancies, but still it satisfies this Roth lower bound for every n element point that it's at least of order log n to the t-1/2. And it's also not a big surprise that the proof for the L2 extreme discrepancy is an adaptation of the proof of Roth's lower bound, also in terms of the Haas series. So I don't want to go into details here. So all three types of L2 discrepancies satisfy this Roth lower bound of order log n to the t-1/2. Now, so remember, we are interested in relation between these three notions of discrepancy. And in dimension 1, we have a very clear picture of these relations. One can show that the L2 periodic discrepancy is exactly square root 2 L2 extreme discrepancy. So they are more or less the same. And they are bounded by square root 2 times L2 star discrepancy. And this last inequality is also sharp if we are considering symmetrized point set as mentioned before. Okay, so all three discrepancies are more or less the same, up to constant. The proof of these relations is very elementary, so one doesn't need any deep idea. One just uses explicit formulas for the three notions of L2 discrepancies that you can see here. I don't want to go into details. These formulas can be easily shown by just applying the binomial theorem to the squared discrepancy function and integrating out the three parts. And one finds after some lines of algebra these nice formulas. In literature, sometimes these formulas are called Warnock times type formulas, but that's historically not entirely correct, since already Coxma had such a formula in the 1940s. Now, taking d equal to 1 in the univariate case, the formulas are even simpler, and after some lines of algebra, you can see directly the relations between these three notions of L2 discrepancy. So no deep idea is needed, it's just some algebra and a very easy result. So that's the picture in dimension 1, but in arbitrary dimension, the problem seems to be not so easy. So now I come to some of our, I would say, main results in our paper, namely exact formulas for the L2 discrepancies of two types of point sets that are very popular in discrepancy theory and also numerical analysis. In first place, Hammersley point set, and later on I will speak also about rational lattices. The Hammersley point set, I think you know the definition, HM with index m consists of 2 to the m elements. The end point is just n over 2 to the m in the first coordinate, and phi 2n, this is van der Corput digit reversal function in base 2 in the second coordinate. Sometimes this pointed is also known as van der Corput net. So this digit reversal function phi 2 applied to a non-negative integer with binary expansion and 0 and 1 and so on, just reflects this expansion at the comma and gives you a point in the unit interval. So this is the Hammersley pointed, and the Hammersley pointed is very well studied in discrepancy theory. We have a lot of very accurate results about distribution properties of Hammersley pointed and of variations thereof. And in particular, there also exists an exact formula for the squared L2 discrepancy of this pointed that you can see here. This formula goes back to the 1960s. Vilenkin, Holton, Zaremba, but a lot of authors come up with new proofs until today. There appear new proofs of this very nice formula. The formula is in terms of the index m, and I would point already here, we see that the leading term in this formula, the dominant term is m to the power of 2, which will cause some problem later on. Okay, so m to the power of 2. Now we tried, and we also succeeded in proving similar formulas for the other two notions of L2 discrepancies. The squared L2 extreme and L2 periodic discrepancies are now given by these formulas, which even look slightly simpler than for the usual L2 star discrepancy. All three proofs are based on these explicit formulas that I showed you before, together with long pages of computation and algebra. It was really hard work, and in the end we were lucky and came up with these formulas. So what can we see here? In contrast to the L2 star discrepancy, we have here the leading term m and not m squared. That's good here, because this m is essentially the logarithm of the number of elements of Hm. Hm consists of 2 to the m, many points. So the logarithm is essentially m. We have here then the logarithm of the points in use, but we also have here on the left-hand side the square. If we take now the square root, we see that L2 extreme and also L2 periodic discrepancies are both of order square root log n, when n is always the number of points from the point set. Okay, so L2 extreme, L2 periodic discrepancies are of order square root log n, which is optimal with respect to the lower bound of Roth. But unfortunately, that's not the case for the L2 star discrepancy. This was well known before, of course. L2 star discrepancy is of order log n, and that's not optimal. So this is a defect of the Hammersley point set, that the L2 star discrepancy is not of optimal order of magnitude. But there are some way out known. For example, it's known that one can apply digital shifts, and there are papers which exactly characterize those digital shifts such that the digitally shifted Hammersley point set again has an optimal order square root log n. But the pure Hammersley point set without any shift or other manipulation, for example, symmetrizing would also work, doesn't has optimal order of L2 discrepancy. From the result for the L2 periodic discrepancy, by the way, we can also deduce that there exists a geometric shift delta such that the geometrically shifted Hammersley point set has optimal order of L2 star discrepancy. But we can also only deduce an existence result. We do not know from our result how this geometric shift looks like. So there is still some work to do if one is interested in this. What we also can infer from our exact formulas is that the L2 star and L2 extreme discrepancies are not equivalent in general. this is in contrast to the L infinity case. By the L infinity case, it's well known and it's an easy exercise in discrepancy theory. When you give a lecture, it's for sure an exercise in one of the first hours that I use the classical notions here. The L infinity star discrepancy is bounded by the L infinity extreme, which in turn is bounded by 4 times the L infinity star discrepancy. So for the L infinity case, these two discrepancies are equivalent in this sense. But this does not hold for the L2 star and the L2 extreme discrepancy. So there's a difference between L2 and L infinity. So we also studied rational lattices, which can be defined as follows. We are considering a real number alpha with continued fraction expansion given here. That's not so important. Important is that we have an infinite number of convergence Pn over Qn in the continued fraction expansion. And the lattices L and alpha are now defined as the point that you can see here. They're consisting of Q to the n. So Q to the n is the Qn is the dominator of the convergent. And the kth point is k over Qn in the first coordinate and fractional part of k times this convergent in the second coordinate. Also, this type of point sets, these lattices are very well studied and often studied in discrepancy theory. And also for this type of point set, we have an exact formula for the L2 discrepancy, which was proven in 2012 by Dimitri Pillichshammer, by Temlyakov and you. You can see here this nice formula for the squared L2 discrepancy of point sets of the type given above. Maybe on first sight it looks slightly a bit complicated or confusing, but it's not the case. Everything is explicit here. We have here 1 over Qn squared essentially. Then we have a finite sum. R goes from 1 to Qn minus 1 of this trigonometric term here, depending on Pn over Qn. This D of P and Qn is an inhomogeneous Dedekind sum. I don't want to give the exact definition, but also this is a finite sum of Qn minus 1 many terms. So really everything is explicit, and the formula can be computed explicitly for any instance of Pn and Qn. And also we were able to extend also this result to the other two notions of L2 discrepancies, to the L2 extreme and L2 periodic discrepancy, or better, the L2, the square of this discrepancies is given by the formulas, which again look slightly simpler, easier than for the classical star discrepancy. We again have such trigonometric sums, 1 over Qn squared here, and these Dedekind sums are missing here. So it's really slightly simpler. And now we consider one special or famous representant of this rational lattices, which is the Fibonacci lattice, which is obtained by choosing alpha square root 5 plus 1/2. Then it's well known that the conversions are given by Fn minus 1 over Fn, where Fn is these are the Fibonacci numbers. And then these terms, these trigonometric sums that appear in the discrepancy formula is known to be of exact order when we have here Fn of exact order n. And the coefficient of this exact order is also known exactly from a work, from a paper by Benze-Border from 2017, is 4 over 15 times square root 5. And from this knowledge and our formulas, we can deduce the following for the minimal L2 discrepancies. So we study L2 discrepancy, normalize it by square root log n, square root of the number of points, and take the infimum over all n element point sets in the unit square. And the lim inf when n goes to infinity is then bounded by some constant eta. Or for the periodic L2 discrepancy, we have 2 times eta. And the values of these numbers ether, 2 times ether, we obtained from the Fibonacci lattice. Okay, so these are attained for the Fibonacci lattice. A similar result is known for the L2 star discrepancy. That was comes also from the paper of Pillichshammer and Yu, who showed us for the similar expression for the L2 star discrepancy, a similar bound is bounded square root 2 times ether, and this is this number. And what's interesting, this is at the moment the smallest value in dimension 2 for a point set for the L2 discrepancy. Okay, this is at the moment the smallest known number. This gives more or less the coefficient of the square root log n term in the discrepancy bound. Okay, and here this number, the right-hand side, comes from the symmetrized Fibonacci lattice. The symmetrized Fibonacci lattice gives here this number. So one can say at the moment that the symmetrized Fibonacci lattice is the two-dimensional point set with the lowest L2 discrepancy, up to some lower order terms. What else can we see from our discrepancy bounds formulas is a nice connection between L2 periodic and L2 extreme discrepancy. If P is either the Hammersley point set or any rational lattice, then these two kinds of discrepancies are related by this formula here. Okay, and one might have the hope, okay, maybe this formula holds for any point set in the two-dimensional unit cube. But that's unfortunately not the case. One can easily find a counterexample where such an identity does not hold. The counterexample are simply regular grids. Regular grids in the unit cube don't satisfy such a bound. So it's not valid for arbitrary point set, but it's interesting that it holds for Hammersley point set and also for any lattice, any rational lattice. So several questions remain, and I state here two of them. The first question is about the relation between L2 extreme and L2 periodic discrepancy. In particular, are those two types of discrepancy equivalent? So remember, we know L2 extreme discrepancy is bounded by L2 periodic discrepancy, but can we bound also L2 periodic discrepancy by some constant time L2 extreme discrepancy? That's one of our questions that we couldn't solve so far, which is still open. Another question is about relation between L2 periodic and L2 star discrepancy. Is the L2 periodic discrepancy dominated, maybe up to some constant, by L2 star discrepancy? So remember, we know this in dimension 1, L2 periodic discrepancy is bounded by square root 2 times L2 star discrepancy. But in the case of bigger dimensions, dimensions d greater or equal to, this doesn't seem to be very easy, at least. So these are two questions that we have. Remember also L2 discrepancy, L2 star discrepancy is not equivalent to L2 extreme and L2 periodic discrepancy. That's also what we can deduce from our formulas. So here you have a concise picture of the two questions that I stated just before. In the general dimension, L2 extreme we know is dominated by L2 periodic and L2 star discrepancy. But are there any of these are equivalent, and what is for L2 periodic and L2 star discrepancy? So this is a big question mark at the moment. The picture is clearer or almost complete in dimension 1. So I'm already close to the end of my presentation. In the last few slides, I would explain or talk about a slightly different viewpoint in discrepancy theory, namely about tractability properties. I study now the normalized discrepancy, where we normalize by n the number of points. Okay, and from our results or in discrepancy theory for the normalized discrepancy, we are interested in sequences or point sets such that the normalized discrepancy goes to zero very fast. And we have, in many cases, optimal results in an asymptotic sense when the number of points goes to infinity for a fixed dimension. But once one has such an optimal asymptotic rate, one can of course ask, okay, how long do we have to wait until we see this nice asymptotic behavior of the normalized discrepancy tending to zero at the optimal rate? And this question is a problem of tractability. Tractability that is studied in the field information-based complexity, short IBC. And I would like to say a few words about this aspect, especially for periodic L2 discrepancy now. So to formalize this problem, we compare the L2 or the normalized L2 discrepancy with the so-called initial periodic L2 discrepancy, which is given by this formula here, and which is just the L2 norm of the volume function of the periodic boxes. And for this special instance, it's an easy exercise. It's easily seen in for an analysis course, an exercise that it's 1/3 to the d half. And what we observe here, that already this initial periodic L2 discrepancy decays at an exponential rate in the dimension. And this will cause some problem later on. Okay. So now we define so-called inverse of periodic L2 discrepancy for an given error demand epsilon between 0 and 1 and dimension d. The inverse of periodic L2 discrepancy is just the minimal number n of points that is needed in order to reduce this initial discrepancy by a factor of epsilon. Okay, so that's the so-called inverse of periodic L2 discrepancy. And of course, this notion of inverse of discrepancy can be also introduced for any other discrepancy in use. And in the general case, I just write n of epsilon d. In a more general context, in numerical analysis, this quantity, the inverse of discrepancy, is also called the information complexity. And we study now the dependence of this information complexity, or the inverse of periodic L2 discrepancy in our concrete case, on epsilon to the -1 and d, when the error demand epsilon goes to 0 and d, the dimension goes to infinity. And of course, we want to have a very slow growth rate of this information complexity, especially in the number d in the dimension. And in this context, it would be desirable to have only a polynomial growth rate. Okay, when we have only a polynomial growth rate of this information complexity on epsilon to the -1 and d, then one says that the discrepancy is tractable, or polynomially tractable. For example, the classical star discrepancy has this property. The inverse of the classical star discrepancy depends linearly on the dimension d, and at most quadratic on 1/epsilon. So the classical star discrepancy is polynomially tractable. This was a surprising result from 2001, I guess, by 4 authors: Stefan Heinrich, Erich Nowak, Greg Wasilkowski, and Henryk Wozniakowski. On the other hand, if this information complexity grows faster than exponentially in the dimension, then one says that the discrepancy suffers from the curse of dimensionality. Also, of course, a disadvantage. That's a property that we don't want to have. So, and we studied what happens for periodic L2 discrepancy, and we were interested in this question, but unfortunately we found that periodic L2 discrepancy suffers from the curse of dimensionality, because the inverse of periodic L2 discrepancy grows exponentially fast in D. So we see we even have a bound from above. That's for this assertion not so important, but it's essentially 3/2 over T. So exponentially grow rate for the inverse of periodic L2 discrepancy, which means that it suffers from the curse. That's bad news, but that's how it is. On the other hand, of course, the result didn't come as a big surprise to us, because a similar result also is valid and for the L2 star discrepancy. This was shown by Henryk Wojciechowski in 1999, and the inverse of the L2 star discrepancy grows at least like 9/8 to the power of D. So also L2 star discrepancy suffers from the curse of dimensionality. What is true for the third notion of L2 discrepancy? We do not know so far what happens for the L2 extreme discrepancy. Maybe one can look also on this problem, but I do not have too much hope that it satisfies some kind of credibility. The reason for this is that already the initial discrepancy is decays like 1/3 to the D. Okay, that's the real reason here for this defect of the periodic L2 discrepancy. So with this short excursion to tractability theory, to information-based complexity, I would like to stop for today, and I thank you very much for your attention.
Any questions for our speaker?
I have a small question. Maybe the 9/8 here. Do you believe that it can be improved to 3/2, similar to the other case, periodic discrepancy?
Good question. I don't know.
Okay.
One has to look into the proof. Maybe, but you see, we infer the curse of dimensionality here, and so the motivation was not that big to recheck all the proof, but maybe that's possible. Yeah.
Okay, thank you.
Other questions? All right, well, then I suppose if not, let's thank the speaker again.
Okay, thank you very much. Thank you for listening.
I will stop the recording now.